There's an invention out there that's, well, it's one of the most important ever, but you've probably never even given it a second thought. It's this simple, incredibly powerful engine that runs just about every factory, pump, and fan in our modern world. So what is it, and how on earth does it work? Let's dive in. So this is it, the three-phase induction motor. I know, it might not look like much, but this thing is the unsung hero of our entire industrial backbone. It's inside the systems that cool our buildings, the pumps that move our water, and the conveyor belts that bring us pretty much everything we buy. It is truly the workhorse of our modern world.
So the big question is, how does this thing actually work? How does a device with almost no moving parts that even touch each other turn plain old electricity into powerful, reliable motion? That's the mystery we're about to solve.
All right, to really get what's going on, we've got to peek inside. So let's pull it apart and look at the essential components that make this motor tick.
What's really amazing is that at its core, this motor is surprisingly simple. It's really made of just four main parts, all working together in perfect harmony. You've got the stator, the rotor, the housing, and the end shields. Let's take a closer look at each one.
Okay, first up, we have the stator. And just like the name suggests, this part is completely stationary. It doesn't move. It's basically a ring of steel with a bunch of copper wire coils wrapped all around it. When we pump electricity into these windings, they create a rotating magnetic field. And that rotating field, that right there is the key to this whole thing.
All right, now for the part that actually spins, the rotor. And this is where the motor gets its famous nickname, the squirrel cage motor. You can see why, right? The core here looks a little bit like one of those hamster wheels. It's just a series of conductive bars all connected by rings on either end. Super simple.
So they take that squirrel cage, and it gets encased inside a cylinder made of thin, laminated iron sheets. This whole thing forms the complete rotor, the very heart of the motor. And get this, there are no wires, no direct electrical connections to this thing at all. It just sits there inside the stator, ready to spin.
Now, obviously, you can't just have these parts sitting out in the open. They need some protection, right? That's the job of the housing. But it does way more than just protect it. See those fins? They're not just for looks. They act like a radiator on a car, pulling heat away from the motor to keep it cool while it's working hard.
So, when you put it all together, you have the stator and rotor sitting inside the housing. Then you have end shields that hold the bearings, which let the rotor spin freely. And a lot of the time, there's a fan attached right to the shaft that blows air across those fins for some extra cooling. It's simple, it's elegant, and it is unbelievably effective.
Okay, so we've seen the pieces of the puzzle. But now for the real magic, the physics. How does electricity in the stationary stator make the completely separate rotor spin with no physical connection? Well, it all comes down to a fundamental principle of science.
And that principle is called electromagnetic induction. The core idea is actually pretty simple. If you have a changing magnetic field near a conductor, like those bars in our squirrel cage, it will induce an electric current in that conductor. It's like magic. No physical contact is needed at all.
This whole dance happens in four main steps. It's actually a really elegant process. First, the stator creates that rotating magnetic field. Second, that field induces a current in the rotor. Third, the current in the rotor creates its own magnetic field. And finally, those two magnetic fields push and pull on each other, creating the force that makes it spin. Let's see it in action.
Okay, step one. We pump three-phase AC power into the stator's windings. You can think of it as three separate, synchronized currents that are all slightly out of phase with each other. This energizes the coils in a perfect repeating sequence, creating a magnetic field that doesn't just flicker on and off, it smoothly rotates around the inside of the stator at a constant speed.
Now, for steps 2 and 3, so you've got this spinning magnetic field from the stator. As it sweeps across the rotor bars, which aren't moving yet, it induces a powerful electric current in them. That's our electromagnetic induction right there. And of course, that flowing current immediately creates a second magnetic field, this one centered on the rotor itself. And here's where the magic really happens. We now have two magnetic fields, the rotating one in the stator and the new one we just created in the rotor. And just like when you try to push two magnets together, they attract and repel each other. This interaction creates a powerful twisting force, what we call torque, on the rotor, forcing it to spin as it tries to line up with the stator's moving field.
But here's the really clever part. The rotor can never quite catch up to the speed of the stator's field. There's always a slight difference in speed, and that difference is called slip. And slip is absolutely essential. Remember, induction only happens when the magnetic field is changing relative to the conductor.
If the rotor moved at the exact same speed, the field would look stationary to it, the current would stop, and the whole force would just disappear. It's this constant chase, this almost but not quite, that keeps the whole thing running. Isn't that wild?
So, we get the how, but why this design? Why did this one specific type of motor become the absolute king of the industrial world? The answer is in the sheer genius and simplicity of its construction.
I mean, just look at this list of benefits. It's incredible. The design is super robust and can handle tough conditions. It's highly efficient. But here's the big one. Because there are no brushes or physical contacts wearing out, there's almost zero maintenance. They're cheap to manufacture, they give you tons of power right from the start, and they're self-starting. Just flip a switch and they go. It's an engineer's dream come true.
So, with a resume like that, is it any wonder these things are, well, literally everywhere? Let's take a quick tour of just a few of the places you'll find these unseen workhorses doing their job.
You've got massive industrial pumps, for one. They're moving huge amounts of water, chemicals, you name it, and they do it with incredible reliability day in and day out.
Just look up. Next time you see a big office building or mall, look at the roof. Those giant HVAC units keeping everything cool? Yep, the fans and compressors inside are almost certainly powered by three-phase motors.
And think about every factory or warehouse you can imagine. These conveyor belts that are the lifeblood of manufacturing and logistics, that's our motor doing the heavy lifting, moving products all day long.
And then you've got the real heavy hitters, like industrial mixers. That immense power needed to get a huge vat of thick material moving from a dead stop, that's that high starting torque we were talking about, and it's absolutely essential for jobs like this.
From farms to skyscrapers, this simple device, born from a brilliant application of physics, truly does power our world. It's a testament to elegant, effective engineering. So, from now on, whenever you hear that distinct hum of a big machine kicking on, you'll know exactly what's happening inside. The only question left is, where are you going to spot one next?